Okay. Welcome everybody to Chennai. We are delighted to have Professor Prajakta and Nimbhorkar from Chennai Mathematical Institute visiting us. Prajakta is visiting us after a hiatus of 17 years. Prajakta is possibly the senior most EFR affiliated person in this room, possibly even in all of SKCs. I think only Pranav and Raja have affiliations. So Kavita. Once you graduate, your affiliation, right? You are released. Prajakta did a master's at IIT Bombay. She started her PhD over here, which then transferred to Institute of Mathematical Sciences, where she did her PhD with Professor Meena Mahajan. Prajakta works in multiple areas. She works in she started off with an area in complexity theory, space related partition, but she's more active these days in matching and fair allocation and stuff, and she's going to be speaking on one of these topics. EFX from agents to types of agents.
Thank you. I'm delighted to be here after many years. Hopefully, you will have something to get from the talk. And of course, anytime feel free to stop me and ask questions. So the setup consists of fair division of indivisible items. So we have a set of n agents, and there are m indivisible items. And each agent declares a valuation function over subset of items. Every subset is valued non-negatively by every agent. And in this talk, we will focus on the additive valuations. So the value of a subset for any agent is just sum of values of the individual items. And what do we want to do? We want to partition this set M among the n agents. So here xi is the subset of items that the ith agent gets. And we want this allocation to be fair. We call x1 to xn as the bundles which are given to agents, 1 to xn. So what is fair that we will come to. So one notion which is the ideal notion of fairness in some sense is envy-freeness. So we say that under this notion x is fair. If for every pair of agents ij, every agent values her own bundle at least as much as anybody else's bundle. So there is no envy from any agent I to any agent. But then the question is, can we always achieve this? And the answer is a trivial no. For example, then we have 2 agents and just 1 item.
What is known to the person who is designing this? They know all the valuations or?
Yes. So we assume that here everybody has a complete information. So
okay.
Well,
it's feasible because you're an additive model, not.
Yes, if it is non-additive or something other than additive, then we have to have an oracle.
Okay.
So
Are you talking about efficiency? I thought this was just existence.
Yes, but
then why does it matter if it's additive or not?
No, additive, you might use additive for other properties, but here you can also talk about. If you don't care about efficiency, it doesn't matter whether you're given the whole thing or this one, but additive might be useful for other.
Yeah, definitely. But it's not about the information is not there.
yes, so in fact, these things although we say existential, they will turn out to be pseudo polynomial times. Not that efficient is completely absent, but they're not as efficient as we would like.
For additive.
Yes. So one realization of envy-freeness that is being considered in literature is envy-freeness up to any good. So I will use good and item interchangeably, but they mean the same thing. So this notion was proposed in 2016. And we say that an allocation X is EFX or envy-free up to any item. If for every pair of agents, ij, I might envy j, but the envy of I will disappear if any one item is removed from j's bundle. And if this doesn't happen, then we call it a strong envy. So equivalently, an allocation is EFX if there is no strong envy between any pair of agents. So let me just give a quick example. So here we have two agents A1 and A2 and three items given in value and these denote the values of the items that the agents assign. So it is not difficult to check that this is an EFX allocation. Although agent A2 envies agent A1, if we remove either G1 or G2 from A1's bundle, this envy disappears. And even A1 envies A2 here because although A2's value for her own bundle is 8, A1 assigns 14 value to that, which is more than this 13. So in fact, both envy each other, but it is an EFX allocation. Whereas this one is not an EFX allocation. So here A1 assigns a value of 8 to her bundle, whereas a value of 15 to A2's bundle. If G3 is removed from A2's bundle, then the envy goes away. But it doesn't go away if G1 is removed. G1 is removed, A1's value for this bundle still remains 10, which is more than A1. So this is a strong envy. And it's not EFX. Yeah, so any allocation with one item is trivially EFX. One item in each bundle is going to be trivially EFX because you remove that item and the value becomes 0. Now the question is, does an EFX allocation always exist? And here we don't know the answer. And this is one of the biggest open problems considered by the pair division community. Anyway, we don't know the answer for every case, every general envy. But we do have some partial results. This is not an exhaustive list by any means, but complete EFX allocations are known to exist for identical valuations, also when there are only two agents. And they also exist when there are at most 3 agents. This was the result by Chaudhary, Garg and Melon in 20. And this result came, I think, soon after that. Soon after that. When there are, so EFX allocations exist when there are at most 2 distinct valuations. So here I said complete, which means every item gets allocated to some agent or other. Here we compromise on that and we say that some items can remain unallocated. Of course, one can have an empty allocation keeping every item unallocated. That's not quite an acceptable thing. Let me come to that point. So here the first result that is known is there is always an EFX allocation that leaves at most n-1 unallocated goods. Note that n is the number of agents and the number of goods could be much larger. At most n-1 remain unallocated. Not only that, no agent will envy this unallocated goods bundle. So this should not be a valuable subset for any agent. So this is the word used for this is charity, and what goes to charity is not envied by anyone. A slight improvement came later when n-2 unallocated goods could be managed. And the same paper also has EFX allocation for 4 agents where
For charity, is it that it's not envied or is it not strongly envied?
it is not envied.
Not envied.
Because if individually if any agent envies that bundle, then they can simply exchange and give the lower one to charity. This cannot happen indefinitely.
But their bundle may have more goods.
But it's about value, right? So if someone envies charity means that bundle is more valuable for that agent than her own bundle.
But I thought the point was that the size of the charity is small.
Yes, in that case we can continue the allocation. So if there are more than n unallocated items, we can always allot some and maintain EFX properly. So this paper also contains another result that is EFX for 4 agents with at most 1 item unallocated. Then there are notions of approximate EFX. What I mean by approximate EFX is Vi of xi is not quite greater than equal to Vi of xj minus g, but it is that whatever 0.618 fraction times this value is still smaller than the value that I assigns to own bundle. So here is the relaxation. So earlier we were asking that Vi of xi should be more than equal to Vi of xj minus g. Now we allow a small fraction to be multiplied.
What happens if you have approximation to the original envy thing? Or that's not not EFX.
Even then, if you have one item, you will have it. Like,
You can have even any constant approximation.
yeah, because somebody has the item, somebody does not.
Oh, okay, okay.
Similarly, there are results where we get arbitrarily close approximation to EFX, but the number of unallocated goods depend on that epsilon factor. And there is also two-third EFX known for most 7 agents, came quite recently. So we generalize some of these results, and let me state what we prove. So we prove that EFX allocations exist when there are at most 3 distinct valuations. So here EFX is known for 3 agent or 2 distinct valuations. So we improve on both these fronts and prove it for 3 distinct valuations. Also for k distinct valuations and k minus 2 unallocated goods, we show that EFX allocations exist, which improves as in generalizes this result to number of agents instead, as in number of agents which have a valuation function as opposed to just the number of.
I didn't read it. What was the other, what was the second result?
This one.
K distinct valuations and K minus, okay, got it.
So there are only 3 distinct valuation functions, but each valuation function can be there for many agents. There need not be 3 agents, but they all pick one of the 3 valuations. And the open questions are to get EFX for 4 or more agents. From our results, which generalize from number of agents to number of valuations, the question is, can we prove a meta theorem, like if EFX exists for k agents, then it also exists for k valuations? We don't know the answer to this because we are not able to use this as a black box. So in this talk, I will talk about EFX for 3 valuations. We call it 3 types of agents. Is there any question so far? So the high level template, which is used not only in our work but also the 3 agents work, is that at every step we maintain a partial EFX allocation, which is X. And to start with, this allocation can be anything where there is one item in each bundle, which is trivially EFX. Then as long as there is some unallocated item, we apply some update rule and update X. And this goes on and on. And of course, this while loop will terminate only when there is no unallocated item. But of course, it should not go on indefinitely. So we have to show that every iteration makes progress or any update rule, which brings improvement in X at every iteration. So the question is, what is this improvement?
So this is only for the first result, for the at most three valuations, not for the second. Or you said.
That will also go.
This is a general template here.
No, but the general template, how does that loop end? Because there's going to be at most k minus 2 on unallocated goods, you know?
Yes.
It could be that some of those goods get put into charity. Because charity is also, okay.
Yeah, so in that case, unallocated goods case here, it will stop as long as, I mean, whenever there are only k minus 1 allocated goods and they are not envied by anybody. So one update rule is Pareto improvement. So this says that if y is the allocation obtained by applying update rule on X, then y is EFX. And moreover, no agent gets a worse bundle in y as compared to X. And also, at least one agent gets a strictly better bundle in y as compared to X. So nobody is worse, but someone is better. Then that is called Pareto improvement. And we denote that y is a Pareto improvement of X. This is the notation that we will use. Also, this seems too strong because no agent can ever worsen. But this has actually been useful in some results. So first of all, this will eventually terminate because at least one agent has to improve and even that cannot go on indefinitely. It also works for some partial or approximate EFX results. In particular, that n agents and n-1 or n-2 unallocated items, Pareto improvement works. As it turns out, it doesn't work for 3 agents case. And in fact, this paper has a counter example where every partial where there is a partial EFX allocation, which is this Pareto improvement wise better than any complete EFX allocation. So if we want to go from partial to complete, the value has to go down for some agent. So what do they use for free
But
agents?
could it be that you start with the allocation you start with, it is such that you never reach those bad examples in that paper?
I mean, this is like you give one partial allocation.
I
where-
see, it's just a one step, you're not progress if you reach there, they don't say that, okay.
So they exhibit one partial allocation from which you can't reach a complete allocation without reducing the value of on agents. So
In particular, you could have, there could be a better starting point and you could have, you could have started off with the.
It's that you never encounter such partial.
but then it's not clear how to avoid such cases. We don't know what leads to that. Okay, so the question is, what do they use if not Pareto improvement? So they use a weaker update rule, a weaker improvement, where they look at this lexicographic, they look at the lexicographic potential function. So for three agents and VA, VB, VC as their allocations, they look at this tuple VA of XA, VB of XB, VC of XC. And the update rule is that if Y is obtained by updating X, then the potential of Y is strictly more than potential of X. So here, for example, if A is improved, then these two can go down and still we have a Lex improvement. As it turns out, we don't know how to even get Lex improvement in our work, where we have three valuations in VA. So our potential function is different. So we have groups of agents A, B, and C. Agents in group A have valuation VA and so on. And the potential function is we just arbitrarily pick one group and the minimum bundle in that group, the value of that bundle forms our potential. We show that this will keep on increasing as long as there is an unallocated.
And so for the three agent case, you're only going to focus on A's value for A's bundle.
For three valuations case, yes.
Yeah, okay.
A's value for A's bundle, but there are many A's because this here there are.
But if it were only three, the restriction to the three agent setting,
Yes, it
that
could
would
be.
be, okay.
And for the potential,
Go ahead.
so for the potential function, you can pick state B also, right?
Yes, anyone, but we can't change it in between. Once we pick it, it has to be there.
I don't follow, so this potential function does not depend on B and C?
No, but we also ask for EFX, right? So automatically A cannot be improved too much without improving B and C.
As you say, you pick one of those three and you just say what is the minimum agent in that class, okay, fine.
And your thing works, whether you pick calligraphic A, calligraphic C, or there, you'll show that one of them is a,
No, any of them.
any of them can.
Okay, so I will first talk about some techniques that we borrow from earlier work. So one is what is called as envy cycle elimination. So here, if we have an allocation X, then we draw an envy graph where vertices correspond to agents. And there is an edge between I and J, AI envies AJ. So I will use A1, A2, A3 and so on when there is a general number of agents. Whereas if I talk about only three agents, I will use A, B and C. So this works for any number of agents. And this is how we will draw the envy graph. So suppose this is the envy graph. And this envy graph has a cycle. So because the agents cyclically like the other bundle better than their own, we can actually do a shift of these bundles along this cycle. And we can eliminate it. So A1 gets X2 because A1 prefers X2. Then A2 gets X3 and so on. Now A2's bundle improves. So this envy may or may not remain. That is why I have drawn it dotted. For A6, A6 preferred X4 over X6. So this envy will shift from instead of A4 now A6 will envy A2. But then as long as there is a cycle in the envy graph, we can do this. And this is again a Pareto improvement because these four agents improve and these two don't degrade. So we will here onwards assume that the envy graph is acyclic.
So your potential function is Pareto and it is the ABC one. It is either or.
Yes, so if we don't increase potential, at least we should get a Pareto improvement. Okay, so then there is another technique which is called as champion. So here there are, this again works for any number of agents, although I have shown only 3 here. So A1, A2 and A3 have certain bundles. And this is an unallocated item G that we are trying to give to one of the agents. Suppose to A1. And we ask if A1 is given G, is there anybody who will strongly envy this X1 union G? So if nobody strongly envies, of course we can give it and proceed with another item. But if one or more agents strongly envy A1 after getting this X1 union G, then we ask among the agents who strongly envy, who envies the smallest subset of this. So clearly because let's say A2 and A3 both strongly envy. So any item is removed from X1 union G, the envy will persist. That is what in by definition of strong envy. Then what if we remove another item and another item and so on? So what is the smallest subset that anybody envies of this X1 union G? And whoever envies the smallest subset is called as G champion of X.
Okay.
And the subset we call as the G champion subset. Now clearly nobody envies a G champion subset because no one strongly envies G champion subset because then that agent would envy even a smaller subset of it. So by definition, this would not be the smallest envy subset. And in fact, an agent can champion herself because it may happen that A1 likes a much smaller subset of X1 union G because G is very valuable for A1. Maybe A1 likes only G compared to X1. That can happen. So an agent can also self-champion. And suppose A1 self-champions, then the smallest envied subset S can be given to A1 and A2 and A3 can retain their bundles. So this S is still better for A1, whereas this is not strongly envied by anybody by the definition of champion. So this will be a Pareto improvement over our current allocation. So whenever an agent self-champions, that is the smallest subset of that bundle union G, that is liked by the owner of that bundle itself, then we get a Pareto improvement. So here onwards, we will assume that we don't have any agent self.
So in this situation, like the number of unallocated items that might actually go up, right, with the process.
Yes.
Okay.
So that is why we can't say that in every iteration one item will get allocated and then we will terminate in every iteration.
So here you are saying that A1 strictly prefers S over X1, right? Okay.
So the smallest envied subset of X1 union G, that is S, this even A1 envies when compared with X. Of course, multiple agents can champion, but that doesn't matter. The thing is that this set is a safe set in the sense that nobody strongly envies it. Whenever it is given to someone, we can say that there is no strong envy towards that. So we come to some cases which are, again, this is a general case which works for any number of agents. So consider the case in the NP graph has only one source. So the picture looks something like this, not necessarily a path, but the source is only one. And we ask if there is an unallocated item G, we ask who G champions X1. Again, if A1 G champions X1, that is A1 self G champions, we get a Pareto improvement as we saw earlier. So the interesting case is when someone else G champions. So for example, let's say A3 G champions X1. So the smallest subset of X1 union G, that is anybody, that anybody is actually A3. In that case also we can go for a cyclic shift because A1 can be given X2, A2 can be given X3 and A3 can get whatever smallest subset of X1 union G that A3 is. So this cyclic shift is there. Now again here these three agents improve and A4 remains the same. So this is again a Pareto improvement. This figure shows the improved findings. Okay, so new allocation is EFX and so Pareto improvement. And it goes for any number of agents. And in fact, this also leads to EFX if all the valuations are identical, because when there are identical valuations, there can't be multiple sources. So now we come to the case where there are multiple sources in the envy graph. So now we will focus on three agents case. So far whatever was there applied to any number of agents, but now we will only look at three agents. So what is shown for agents is that,
But even if there is one source, it is possible that there is no path to the champion. Can that happen?
then there will be multiple sources.
Why? Because
Disconnected components are its SI. So if this component has a source, this component has a source.
It is also SID,
so a source is a vertex.
which has
that-
no incoming
It
edge.
is not envy.
Oh, it has no incoming edge. Okay, fine. I thought it was okay, fine. It doesn't matter if it has no outgoing edge either.
Yes, but again the remaining connected component has to have a source then, because again it's.
Got it.
So for two sources case for three agent envy graph, this paper has an example where at least one agent's bundle value has to go down. As I said, there is no complete EFX allocation which Pareto dominates the partial one. However, what they show is for every agent, we can find a complete EFX allocation where that agent includes. So someone's value has to go down, but we can actually choose the agent who improves. And this is very useful for the Lake's potential function, because in Lake's either A has to improve, or if A remains the same, then B has to improve, and so on. So here they show that they can choose the agent that they can improve. So they show that there is another partial EFX allocation. Sorry, this should have been by. So that it is Pareto. This should be Lake's dominant. Okay, now we come to the case when there are three sources in the envy graph. We will modify these cases when we go to multiple types, but I will highlight the modifications. So for three sources case, they get an intermediate allocation Y, which is a Pareto improvement over X, but Y may not be necessarily EFX. But from that, then they have to get to another EFX allocation, which is Z, which is still a Pareto improvement over X. So they look for champion cycles. So consider when there is a 3-length champion cycle. Remember that we are only 3 agents case, so champion cycle can be of length at most 3. So here A G champions X2, B G champions X3, and C G champions X1. Now, of course, we can't give G to everybody, although they like the subset which contains G. So what do we do? So let's say Ti is the subset of Xi, so that the G championing agent prefers Ti union G over own bundle. Okay, so this is X1. This T1 union G is preferred by C. T2 union G is preferred by A, and T3 union G is preferred by B. So I hope the notation is clear. And this is the leftover part of it. Now what we conclude from this championing is that even without G, they like these top parts, so to say, more than compared to their own top parts. So as remember that we have no self G champion. So although A has the X1 bundle split into T1 and X1 minus T1. A doesn't like T1 union G because A doesn't self G champion. This must be a smaller subset which someone else, that is C, is champion. Okay, so no agent self G champions, which means no agent likes this top part union G compared to own bundle. So on the other hand, A G champions X2. So A likes T2 union G over X1. So we get this ordering among the bundles. That is, A likes T2 union G more than X1, but A likes X1 more than T1 union G.
And then you can swap them.
Then we can do a cyclic shift of these bundles. Similarly, we can conclude that B likes T3 over T2 and C likes T1 over T2. So this is a strange thing, that is, we asked about G championing, but actually what we are shifting is G is not coming into picture at all. We are only improving their bundles by a local cyclic shift. Of course, this won't be EFX allocation and we will have to use G later on. That is a bit more technical work to get to an EFX allocation. Nevertheless, so I will leave the three agents discussion there and come to our work where there are multiple
Can we go back
types.
to the previous?
Yeah.
So at the moment, what has happened is there has been a Pareto improvement on the current.
Because everybody gets this better subset compared to earlier one.
Okay. I see.
So A1 likes T2 over T1, so now A1 gets T2 instead of T1, and the rest of the part remains as it is. So this is a Pareto improvement. This might lead to strong enemies, in which case we have to cut down the bundles and maybe reshuffle them a bit again. So yeah, from three agents now I will talk about three types. So A1 to AP are the agents who have valuation BA, B1 to BQ have BD, and C1 to CR they have BC. And we assume there is non-degeneracy in the sense that no agent values two distinct subsets equally. So we are not worried about equalities. This comes without loss of generality, but right now I will not get into that. That is again discussed in this Chaudhary model. So let's make some simple observations when there are multiple agents of each type. First of all, within same group there is no envy cycle because whatever bundle is of higher value, they have a unanimous opinion about that. They can't have a cycle within themselves. And we also sort and rename the agent so that agent A1 has the smallest bundle in any group and they are ordered from A1 to A for the ease of notation. Similarly for B and C. And we call the AB and A1, B1 and C1 as the poorest agents in their group. Let's make, so this is the envy graph. This is actually transitive, but I have not shown all the transitive edges. B1 envies A1 envies everybody from her group and B1 envies everybody. So on. A few observations here. That is, if any AI envies BJ, let's say A2 envies say B1, then A1 is also going to envy because A1's bundle is smaller in value than A2, and the valuation function is the same. So if any AI envies BJ, then A1 also envies BJ. And in fact, same thing applies for G championing. So whichever set, say A2 will G champion, even A1 will G champion that set, or possibly even smaller set. So even though we have lots of agents here, the envy graph can still have only three sources because everybody else has an incoming envy agent. So to get an improved EFX allocation, we focus on A1, B1, C1, but we have to also ensure that while improving them, we don't develop strong envy from other agents. Okay, so we again use champion cycle as in three agents case, but I will highlight what changes compared to what we have seen already. So if you remember the three-length champion cycle, we just did a cyclic shift of the top parts and we got to an allocation Y, which was not an EFX even for three agents. Now, using the same procedure, possibly we can get Z, which is EFX among A1, B1, C1, but it may not be EFX among others. So when we come to this allocation Z, which comes from a procedure similar to the three agents one, how do we get rid of the strong envies? So there are two kinds of strong envies which arise. One is intergroup strong envy. For example, A2 to AP can envy B1 and so on. And second one is intra-group strong envy. That is because A1 improves, A2 can strongly envy A1. I am saying A2, but it could be any AI. So the first one we show that it is not simply possible. So this needs a proof, but what we show is that not only that A1 improves, the others degrade in A1's views and hence in any AI's views. So the new bundle, for example, that B1 gets, in A's view, it is smaller than even the old bundle that A1 had. And hence there is not even an envy from any A2, B1 or C1. later.
This
on
did
yes.
not happen in the origin, or was this also?
There was no question of other agents strongly envy. So this allocation is already EFX among A1, B1, C1, which was okay for the 3 agents case. But now these leftover agents are there, AI, BJ, and CK.
Oh, you're talking about intra-group envy.
This is intergroup, but these are the other agents which are now strongly envying B1, for example. A2 is strongly envying B1 because B1 improved. A2 did not improve.
Yeah.
So the improvement of these agents might invite strong envy from others, from their own group as well as different groups.
But because A1 did not do that, it shouldn't happen for A2 also. Right?
No, but it may not be the case that A1 is still the poorest agent in that.
Now A1 cannot be poorest because A1 improved. So eventually we will sort the bundles, but not yet at this point.
Okay.
So A1, B1, C1 improved, they may not be poorest in their group anymore.
Okay.
And hence, even if A1 doesn't strongly envy B1, A2 can still strongly envy B1. Because A2's bundle now might be smaller than A1's. But then we show that actually that doesn't happen. Not only that these agents improve, they degrade in the view of the other groups. And this is not possible. This doesn't happen and we don't have to resolve. For the intra-group strong envy, it is much simpler to deal with. For example, if A2 strongly envies A1, and suppose there is no intergroup strong envy, then we can say that okay, A1's bundle is too high. If A2 doesn't strongly envy others, then we can also cut down on A1's bundle. So that it is still more than A2's bundle, but not too much to have strong envy. So this cutting down doesn't again cause an envy from A1 to strong envy from A1 to others, because it is still better than A2's bundle. So A2 is not strongly envying others, so A1 will also not strongly envy because we give a slightly larger bundle than A2's to A1. So this cutting down we can do because they have the same valuation. And this envy remains is essential because if we cut down A1's bundle so that it becomes smaller than A2's, then we can't say that A1 will not strongly envy others. Only if it remains larger than A2's, we can say that there is no strong envy from A1 because there is no strong envy from A2. Then there is another technique that we use, which we call as pseudo cycles. So remember that this is our potential function, the minimum value of any bundle in a particularly chosen group. So what are these pseudo cycles? They are not actually cycles. So for example, here is a pseudo cycle where A1 envies Bi, not maybe B1. B1 envies C1 and C1 doesn't even envy but G champions A1's bundle. Now this is not a cycle, but we can do a cyclic exchange here. So how do we do this? So A1 gets this bundle which A1 envies. Then Bi is actually not envying anything, but B1 is envying C1. We can give this C1 to Bi. And then C1 gets the bundle that C1 is G champion. Basically the champion subset of champion. So why is this okay? As in, is Bi improving when we do this? Bi is not envying C1, which means Bi's own bundle is better than C1. But then it is not too bad to get C1 because it is still better than the minimum one in their own group. Okay, so any bundle which is better than the poorest agent's bundle, that could be fine for any group. So if with the bundle that B1 has, B1 is not strongly envying anybody. So C1's bundle is still larger than B1's according to BB because B1 is envying C1. So even with this bundle, there will be no strong envy from Bi to anybody else. So this cycle, although this is not a cycle, there can be still a resolution of this. So this is not a Pareto improvement as opposed to the envy cycle or champion cycles that we were having, because Bi's value is actually going down. But A1 and C1 will actually improve. There are a few more examples of pseudo cycles which I will not get into. The same principle applies here as well. Remember, but one thing to note is that these pseudo cycles always begin and end at A1, so that A1 always participates. So, for example, in some of these cycles, B1 and C1 bundle don't change. But since we want to improve our potential, A1 bundle has to change. So A1 has to participate. We never have a pseudo cycle which has an edge incident on some later agent. That way they are special in for the group field. Okay, so now I come to the two sources in envy graph. It turns out to be the most difficult for three agents. It turns out to be the most involved for us as well. So consider this subcase when A1 is G-championing B1's bundle. Remember that these are the poorest agents. And B1 is envying C1's bundle. Now we have a way to improve A1 because we can give the G-champion bundle to A1 and we can also give C1's bundle to B1. So that can improve A1 and B1. But then what will C1 get? This is not a cyclic exchange. And we can't simply pick any bundle and give it to C1 because that might cause a strong union. So here we have to do several iterations of this while this is a while loop where several iterations go on. So what we do is basically if there is an envy from B1 to C1 or even a champion edge from not B1 to A1 or there is a champion edge from either B1 or C1 to A1, we will have a cyclic shift. So if B1 to C1 B1 to A1 edge is there, then this will be a 2 cycle, we can do a cyclic shift. If C1 to A1 is there, we will get a 3 cycle, we can do cyclic shift. So our aim here is that we will change the bundles of the B and C groups so that eventually they will start liking one of the bundles. So here we also have to cut down on bundles and of B1 of B and C groups, not of A group. Remember that A's bundle we cannot cut down because that is a potential function. We don't want it to go down. But these two we can actually cut down. So how do we do this cutting without creating strong enemies? So currently B1 or C1 don't like any bundle of A. Not just this bundle A1s, but any bundle in the entire group A. Otherwise we could have again had a cyclic exchange as we did in the pseudoset. Okay, so we asked C1 and D1 to pick the favorite bundle outside their own group. So this bundle may not be very nice for them. They might be liking many bundles in their own group and in particular even their own bundle. But we still ask them to pick one which is strictly outside their own group. And for C1 we also give the freedom that okay, you can also choose the one that C chooses. Now if they like different bundles and none of them comes from A, we can possibly exchange them, but not always because if we just keep exchanging, we will keep exchanging forever. So we have to be careful while doing this exchange. If they like the same bundle, here we cut down that bundle. We actually really cut it down, or in case of B, we will actually do a virtual cut down in the sense that we will ask the B1 agent that okay, this bundle is one item is removed from this bundle. This you only mentally assume and cut, and then again pick a favorite bundle. If this is still your favorite bundle, take it without this one extra item that we remove just mentally and not here. So this virtual cutting down happens here, and if B1 still likes that virtually cut down bundle, we just give it to B1. So what changes here? What is the progress measure? I mean, we should keep exchanging forever and the while loop could go on because there is no potential improvement happening here since A1's bundle doesn't change. So here, if B1 or C1 eventually will like a bundle from A because we are doing this cut down. And whenever they like it, we do a cyclic exchange. And then our potential function improves because this champion bundle is actually better for A1. But until then, during this while loop, the pool of unallocated items increases. Because we cut down and again this cannot happen forever. So in every iteration of the while loop, one bundle will be cut down, either really or virtually one. But it will get cut down and no bundle gets cut down multiple times. So it can at most happen as many times as the number of bundles, number of agents in B and C. So this is a bit counterintuitive that this is a progress measure that pool of unallocated items increases. But then it cannot keep increasing forever since the number of items is only 10. And after that, our potential has to increase.
You're not maintaining EFX also, right?
No, we maintain. Because of this cutting down. So, say B1 likes a bundle of some agent in C.
Yeah.
Then if both of them like the same one, we allow C to like that also. As a,
What do you do about the other agents in B and C, about the other members of the group?
so currently we are not shuffled bundles, right? We are just asked which one you like.
Okay.
And then we cut down that bundle. We are okay. So if B1 chooses a bundle, say of that of C1 or any CJ for that matter, we cut down that bundle. We just ask B1 that assume that this bundle is cut down by one item.
Yes.
And now which one do you like?
Right.
So if the same bundle is picked up, which means this is still B's favorite, even if it has one item less. Add that one item to unallocated. So the exchange happens only when it is a favorite bundle for them. And that is still actually what can happen now. That since they are getting a bundle from another group and without regard to their own bundle or their own group, they might have a strong envy towards their own group. So probably that is what you are considering. Yes. But then those bundles we can cut down. Like if this bundle V1 is not strongly envying others from other groups, then we can cut down the other agents bundles. That's
Same kind, yeah.
yeah, that still increases the pool of unallocated items.
In all of this, G is an arbitrary unallocated word. It's not
Yes.
chosen, it's just anything.
Any. So essentially these pseudo cycles and this intra-group envies and this virtual cutting down. These are the things that are kind of new.
So if you did not have these types, would this be the same group as the Bhaskar Chaudhary paper or would it be a different group of three agents?
Actually, they also have to do this sort of cutting down, but then they don't need this virtual update or anything because the cut down has to happen only with respect to two other agents.
So it will reduce to the same argument of that.
Yes. This needs more work in the sense that we don't want to invite strong envies from others. But for them it simplifies a bit, but even that result is, I think there is only one agent. It will, probably we can just use the same thing and can be cast envies. We will not need a virtual update there.
So the part about having at most K minus two unallocated items, that also goes through the same group.
Because that doesn't have these things.
Okay.
There it is simply Pareto improvement. So one second. See, for example, here I have drawn two champion agents. So you have K sources and K unallocated items. You can do a Pareto improvement by asking who champions whom for all those items.
Oh.
So that's you can get K minus one unallocated items.
Okay.
To go to K minus two, you have to classify the cycles a bit more carefully. They call what is a good tree cycle. So that K minus one to K minus two is more work. Essentially, the idea is that you should have as many items as the number of sources in the ending graph. Yeah, so actually that is all. So the big open question is, does EFX already exist?
It's actually a big open.
Yes.
Huge.
So actually there is a counter example for chores where the items are negatively valued and agents dislike them rather than having them. But the valuations are super additive, not additive. Don't have a counter example for chores, even for chores with additive value.
How many agents are there here?
6 or
6.
6 and some 17 items.
Okay.
Yeah, and the question is, there are some new techniques. Are they applicable for any other case? Possibly some more generalization from agents to types of agents. The whole purpose of looking at the types of agents is that to show that the real difficulty of EFX allocation comes because of different valuations rather than because of the number of agents. Although that is very kind of obvious intuition, but this shows that that intuition can be formalized and exploited. So that is all.
Questions? So this, like, do you give you any further results for EFX existence? Like sometimes you can use this to prove more approximations or more.
Yeah, so let me complete this approximation, I mean the known results slide. Yeah, so actually what we think is that this 1 minus epsilon,
Yeah.
this can be generalized and so can this 2/3 EFX. But that is still
And like for the, for the last result, you can replace 7 agents by 7 valuations. Then you see, I see.
so we think that it can happen, but we have not yet written down. Looks plausible.
Okay.
And here also instead of n over epsilon, square root of n over epsilon unallocated pools, we can have k over epsilon. Then
Okay, is number of valuations.
k is the number of. The others are anyway for general number of agents. There is no question of types.
Then the other question, like, is there a result for agents that you don't think can be translated into types or that you?
So again, the results where the number of agents doesn't matter. They just put for any number of agents. Their types wouldn't tell because instead of n agents, if you have n.
Sure. Yeah.
But yeah, for constant number of, the results which are there for constant number of agents.
You think that almost all of them can be translated?
I don't know, maybe there are results which I don't even know,
Sure, yeah, I think.
but. I have not noted a result where there are constant number of agents which doesn't generalize.
Related question, so you had this meta theorem, conjecture, which you did not, showing that if you can, if EFX exists for k agents, then the same results. Rather, if there's a result for k agents, you can have a similar result for k valuation. Do we know at least if there's a theorem of the first type, with a proof style in a particular fashion, then the proof extends to this, that is not a black box statement like this, but if I had a proof of a particular type for EFX existing for k agents, do we know how to extend it to
Like if the proof was based on Pareto improvement.
some such thing? So can
Yeah, I think Pareto improvement is yes, but then it doesn't even hold for three agents.
yeah. No, something which will subsume all your results, which will imply all the results. That is why to believe why this meta theorem holds good. It says all the current proof styles have this feature, hence this one. So is there a can you explain it in that way or?
Yeah, so probably not yet. So this result we had in mid-October or something.
Okay.
And right now we are looking at what possibly can be done from here
Okay.
and whether some such meta theorem emerges.
Okay.
Yeah, I would say it's still work in progress. We are not very
Okay.
in progress.
Any other questions?
So here everything is additive.
Yeah, so actually we may not need full additivity. We need actually cancelability, so to say.
Actually, I haven't seen additivity used anywhere.
No, it was
Yeah.
clear when you
So
cancel
this
it.
cancelability is what is needed. Even if they're not additive, but this cancellation holds. But yeah, we just write it for additive to make things simple. I think cancelability is all that.
More questions?
That's fine.
Thanks for attending.
Sorry, coming. So we can attend.
Thanks for inviting.